Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on foundations of cyber physical systems. So, in the previous lecture we have been talking about methods for reachability verification. We came up with a very basic idea, and we were trying to say that how reach sets can be made, and also we are not going into the actual optimized algorithms that are used, but we are trying to give you an idea that how reach set constructions can be done. There are various optimized algorithms for this. So, what we will do is for the sake of creating some interest in this topic of how to study reachability analysis and stuff, we will take a few examples and we will show you the output of certain tools which are very popular in this domain, which actually do this kind of reach set computation internally and try to figure out if the reach set is going outside some safe zone and stuff like that. So, let us take a very small example. We have a generic, so we have a harmonic oscillator here, as you can see that you are going to give a control force u from outside, and you are if you give the force here, it will overshoot to this side. If you then change the direction of the force, you will overshoot to this side and stuff like that, right. And given the length of this rod as L and the mass of this ball as m, this angular velocity omega will be following this kind of equation, where this angle is nothing but I mean the theta dot will of course be omega, and we have theta, that is the angular displacement of the pendulum, and omega is the angular velocity, and these are the two state variables in this system. Okay, and u is our control input like we said. So, for this system if we try to create a reach set, we use a tool called so this tool you can just check it out over internet. So, this is one of the latest tools that have come up. I mean, this is a very simple one to use. That's why I am talking about this. All you need to do is you have to write a simple Python script where you express the dynamics of the system and some desired property. The tool will just run and it will create this kind of a reach set for you. Okay, and there are several other tools in this domain which does reach set construction, formal verification, and all this stuff. This is just one very simple to use tool. You can just download, if you have some Python interpreter in your computer, you can just download and install and run this thing and get a check. So, you can check that what is the final reach set here. So, this is a plot we are doing. So, in this direction we are plotting the angle, and in this direction we are plotting the angular velocity, and this shows that with time, starting with time, how the reach set has changed. Okay, and as you can see, so I mean initially if you have a very small subset, from that you can start, and these are the possible combinations of theta and omega through which your harmonic oscillator can move about, and it won't ever go outside these reach sets. So, that's an example that we thought would be interesting, but is it all? No. I mean, you can actually use this tool for more important kind of applications also. For example, this is an automotive drivetrain model. So, if you see you have this kind of a gear mechanism which is kind of connecting through these two levers, and it is going to engage each of these gears here, right. So, these numbered indices are referring to the numbering of the additional rotating masses, right, and you have a moment of inertia here denoted by J for this shaft here, and you have viscous friction constants given by B, and and those are used for creating the mechanical equations for the system, which we are not doing, and there is a reference paper which we will provide you. So this one. So I mean, if you look at this paper, it actually contains the detailed analog equations and the controller model for this kind of a system. Let's not get into that. All we are trying to tell you is, if you see that when this thing rotates, this shaft will either connect this way, or if you suddenly change direction, it will connect the opposite way, right? So that's how the clutch mechanism and the differential mechanism will work here, right? And we are trying to show all these different components of the powertrain, gears, the differential here, and the clutch, among others. And so you have a this is a significantly large system, and there are a lot of continuous states here, right? So what can happen is, when these rotating components are going to switch direction, for a short time they will temporarily disconnect. As you can understand that this shaft, once it was driving in this direction, suddenly it changes to the other direction, it will move from here and up to here to engage this opposite direction, this stick here in the opposite direction, right? So in between, what we have here is called the dead zone, and suppose there is an extreme maneuver, that an assumed maximum negative acceleration that will last for 0.2 second, and it is followed by a maximum positive acceleration that is going to last for 1.8 second. Let's say you want to check if that is something safe or not. Okay, so you can actually do a reach set analysis using this tool, okay, where you are trying to create the reach set for the angular position of, let's say, the motor. This is this motor, the angular position, and one of the rotating mass, whichever is engaged here through this gearing mechanism, whichever is engaged, for it, what is the angular what is the angular position. So let's say you are plotting the angular position of these two things, that is the original motor and one of the shafts, let's say the second shaft here, and they are denoted by x0 and x2 here, let's say. So initially it was all 0, right? The motor was at 0, and for the second rotating so the second rotating mass, it's not rotating, but the motor can have a small variance here, as you can see, right? And with time we see that these two quantities can move like this, okay? Their values, their possible set of values can move like this, following this kind of a frontier. And if we simulate further, then with time, once it has started moving like this, then it can switch direction. So this is where the drivetrain which kind of switch the direction, and they both are now going to go in the same direction, right? And if we just want to simulate further, this flow pipe you can keep on building, and you can create this nice graph using this tool, for which you can have this category report from this conference paper. So what I am trying to say is, even in very large industry, specifically the automotive industry, this kind of formal methods can actually be applicable if you try to check for this kind of an engine, for a engine shaft connecting through this clutch and differential to the different gears. If we try to see that, well, under this reverse movement scenario, what are the angle values and what are the maximum differences between these two angle values, and what is the range of those values, is it safe, and all those things. We can actually create these reach sets, and we can just simply verify. So that's one important application I just wanted to touch on. But note that the reach set construction algorithms which were used by these tools are kind of state of the art, and we are not touching them. What we did initially was, in our course, we just tried to give you an idea that how reach sets can be formalized, and how such reach sets can be constructed through this kind of techniques like the post computation and etc. But of course, for using them practically, there are a lot of optimized algorithms which will be employed for this purpose. So fine, from this we will just move on to another model of computation, which is timed automata, which is kind of simpler than hybrid automata, but it also has got its usage. So formally, what timed automaton is just a finite automaton enriched with clocks. So it's very simple. You consider you already know hybrid automata, right? and in hybrid automata we had any kind of continuous variables. Now let us just say that, well, whenever you are having a hybrid automata with a continuous variable, the continuous variable is only having one restriction, that it cannot have any vector field of its choice. If the x is a continuous variable, the differential of x is always 1. If I put on this restriction, what we have is a timed automata. Basically what we are doing is all the variables can only be clocks, and they can be reset like a stopwatch, and they can start counting, something like that. So if we do like that, then we have this kind of a simple timed automaton, right. So let us say you have this timed automaton as an example, and you already know that transitions are equipped with guard conditions, and resets happen on clocks, etc., right. So just for the sake of definition, a timed automaton will have a tuple which is similar to hybrid automaton. You will have the usual set of locations, the set of initial locations, the set of accepting locations. You will have a finite alphabet, a set of clocks, and you will have this. So this set of clocks is whatever originally was your set of continuous variables, and you will have your set of edges. Now when you have an edge, basically it is a transition from one location to another location, and when taking this transition, your clock variables, I mean the continuous variables, they should satisfy some guard condition, and there should be an input event part of the alphabet based on which the transition will happen. And while this transition happens, so the set of clocks, a subset of them may or may not be reset. So that is why you have 2 to the power x here, the power set of all possible subsets of x. Okay. And what are guard conditions? They are just linear relations like we discussed earlier, constraints, right. Linear relations among clock variables with using clock variables and some constant values, right. So the clock variables and some constant values, they will be operated by some of this one of these linear arithmetic operators, and there can be multiple such constants which can be in conjunction. So that is how we define a guard condition. And next we have valuation of let us say you have a valuation. It is also something we have already discussed, that earlier valuations assigned values to any variable, and now it will just assign a value to a clock variable. And with such valuations you can have delayed transitions, like with time just elapsing, your clock variables will just increase by some time tau. And if you have a discrete transition from some state like this, so let us say your location is L, you are jumping onto L prime, there is a guard that you satisfy, that means the valuation right now that you have in L just immediately before the transition will satisfy this guard condition. And when the guard condition has satisfied, then you are also supposed to do the required resetting, right. So after doing the resetting, the valuation will get modified. So as per this formula, right, v prime x will be 0 if they are reset, and they will be v x, that means they will be same because the transition is instantaneous, and in that way your modified state would be L prime v prime. So just similar to hybrid, you will also have a definition of a run of a timed automaton. A run is nothing but, well, you are in a state L0 V0, from there you can have a time elapsing of time T1 tau 1. So that is a delayed transition. So all that will happen is, well, you are still in L0, your valuation will increase by tau 1, and then due to some input event belonging to this set sigma, or that is a finite alphabet of the automaton, you can have a transition to some L1. Now whenever such transitions happens, these rules have to be satisfied, and then again you can have a delayed transition, so that V1 gets updated by tau 2. Then again you can have an action transition or an instantaneous discrete transition. So overall what you have is when you draw that automaton here, you can you can just show like this. In different books you can see that, well, there are different ways to show. For example, here what we are showing is, with respect to this initial location, we are spending here tau 1 amount of time, and then we are taking a transition based on the arrival of the input event A1, right. And then again we are spending some time here, the amount of time we spend is tau 2, and then based on the input action A2 we are doing a transition. So you can show like this, or the other standard that maybe you will see is that, well, there is an location and valuation, then some input A happens at some global time T1, and then you go some other location valuation. From there, then again there is some input A, and which is happening at some global time T2, and based on that it happening. Here we are just showing the delays, the time spent in each case, but this is also perfectly fine. You just show the time at which this input event happened. Then again you go to this some updated state. Again you show the time at which some other input event, let's say B, happened. So that's also quite fine. I mean many books follow this thing also. Okay. So overall these different time sequences, I mean you can look at these runs as a collection of the time spent in each of these states, this time spent in each of these states, or you can also look at it as those global time instants when these transitions were taken. Let's say this happened at tau 1, this happened at T1, this happened at T2. So essentially T2 is nothing but tau 1 plus tau 2 if we are considering this representation, and T2 here in this representation is nothing but tau 1 plus tau 2. Next, if we have a T3, right, it is nothing but tau 1 plus tau 2 plus tau 3. So either you write those absolute time sequence, that is one idea of representing the time sequence, or you just write the sequence of intervals spent in each of these discrete locations, right. So that's also a way to represent the time sequence. Both are fine. Now, when you have such time sequences and with them these input events together, like written like a string, then what you have is what we call as a timed word. So just like a finite automaton will have an input string, a timed automaton will have a timed word. Basically it will be a string where each element of the alphabet will also be paired up with a timestamp, that this is when it happened. Now that timestamp can be based on this semantics of the global timestamp, or the timestamp can be based on the intervals, the amount of time spent in the previous location, something like that. So then we talk about accepted timed word. So let's say you have a timed word, and based on that timed word you simulate your timed automaton, and your timed automaton will have a run something like this. Okay. And at the end of the run, if you are reaching an accept state, right, then we will say that, well, this is an accepted run, or this is this timed word is a member of the language of the automaton. So this is a simple example, like this is a word which is an accepted time word, and with respect to this word, if you just simulating this automaton, and if it is going to eventually reach. So we have some things missing in this picture. Sorry, let me just correct it up. It will be the reset sets, and here the reset sets are blank. Yeah, sorry. So if you can see here, you have one example. So if you are at L0, you can either take this self loop based on an input event A, and you have two clock variables x and y. So you can take this self loop provided the time of y is 1, or otherwise if B comes as an input event, then whatever is the time of y and whatever, I mean, as long as x is positive, you can just take this self loop. Okay. Now from L0, based on an A, you can also move on to L1, and while you do that you will reset x, and when x is again elapsed to 1 and if a B comes, then you can move on to L2. Okay. So let us say L0 0 0, so when this is your initial state, you are in the initial location and all the clocks are just at 0, right, and then there is a B one input event coming. Okay. At this after an elapsing of time, that is 0.1. Okay. After an elapsing of time, that is 0.1, an input event has come B. So what you do is you take this transition, right, and while you take this transition, so x will climb up to 0.1 and y will be reset as per this. So y remains 0, right, and then after this transition, let us say you spend another 0.2 amount of time here, and then a B event comes again. Okay. So with that B event, what will happen is, well, x will again climb up from 0.1 to 0.3, addition of 0.2, but again y is reset, so you are still here. And now suppose an A event comes when after an elapsing of time equal to 1, So, as you can see that with A coming and with time equal to 1 being spent in this location. So, your x at this moment, so at this moment when this is being happening, your x is what? Your x is 1.3 and y is 1.0, right. So, what happens is which guard do you satisfy? Well, the event is A. So, you have to take this transition or this transition, but with y equal to 1 you are satisfying this guard also, right, and here there is no guard to satisfy, here you do not have any guard to satisfy. So, let us say I take this transition, this is a non-deterministic choice, I could have taken any word, I take this transition. Okay. So, I satisfy this guard, nothing is being reset. So, I am here again with 1.3 and 1 as clock valuations of x and y. Now, let us say after spending another 0.2 second, let us say I have an event B that comes. So, again I am in L0, I have taken this self loop. Now, again you will have a y being reset and x has climbed up to 1.5. Now, let us say an A again comes. Okay. Now, you see I do not satisfy this guard, but here there is no guard. So, I can always take this transition. So, I choose to take this one. So, now I am in L1 and both might see y was reset here, and then immediately I mean when I took this transition y was reset, and then you see this is 0, that means I did not spend any time in this transition in this state. I immediately had another A came. So, B came and immediately after that A came, that is what this is being modeled by this 0. So, with B I climbed up here, I got y being reset, and then with A I immediately moved up to L1 and I got x being reset. So, both x and y are 0. So, as you can see that these are instantaneous transitions and here there you do not have any delay, okay, but there is a sequence, that is why you came from here to here and then you came from here to here. So, you have two consecutive instantaneous transitions. So, L0 to L0 and then again from L0 to L1, and but in that sequence, although they are instantaneous, they are in that sequence, right. So, you can understand these things, these issues of having instantaneous but sequences and etc., they will again lead to Zeno conditions like just we had in hybrid automata, but we have already discussed that there. We are not discussing hybrid or I mean Zeno time divergence etc., in the context of timed automata. You are interested, if you are interested you can just consult the relevant material that we will cite here. Okay. So, from here if another event comes after another time elapsing of 1 unit of time, then you see that I go to L2, but when I go to L2 then well I satisfy this guard because x is equal to 1. So, and I land up here. So, this is like an accepting run, right. So, that is how a timed automata typically will simulate. Now, just like hybrid you can have location invariance, like for example, if you are here and you are waiting, you are spending 3.2 amount of time, the invariant will get dissatisfied, right. So, then you are kind of going to be pushed out of the state, right. If you are here after you elapsing of time for 1.1 unit, and then fine, your variables, the clock variables will get updated, right. So, here we have a small example of job shop scheduling. We will show you some few examples of timed automata based modeling. So, for example, here we have a job shop scheduling problem and how that is being modeled here. So, we are trying to show a factory where there are a set of people who are hammering nails, okay, and we are trying to have a automata based specification of when exactly they work and how much they work, stuff like that. So, they can be in any of these two states, they can either be resting or they can be working. So, this is an automata which kind of nicely captures different constants on that. So, let us say I do not allow them to rest for more than 10 minutes. So, that is how I model it, but they must rest at least for 5 minutes. So, that would be a guard here. Then with the start event they will start working, both the clocks x and y will be reset. During work they have again a specification of how much they should work. They must hammer one nail every 4 minutes. So, that is specified by y less than 4, and whenever they hammer one nail there is a hit event, right. But at the same time they should not be hammering a nail too fast because that can kind of compromise your work quality, right. So, you should not hit more than one nail in every minute, right. So, whenever you are hitting the nail y, this value that has been reset after the previous nail was hit, right, this must have time elapsed at least by 1, right. So, you do not hammer more than 1 inside a minute, that will be classified here, and at the same time you must hammer 1 inside every 4 minutes, that is kind of captured in this location environment. Overall, the person cannot work continuously for more than 60 units of time in minutes, let us say, then you cannot have you can have a invariant like this here, right, y less than equal to 60. So, cannot work more than 60 like that, and then when this done event comes, you have to transit to rest. At the same time, while I cannot work more than 60, I must work at least for minimum 40 units of time. So, if I want to specify that, I can have a guard like this here. So, you see that lot of timing specifications, that is the point here, lot of timing specifications of real time systems can be captured by using a timed automaton. As long as only time is the continuous variable, timed automaton is a fine modeling formalism. So, let us pick up some other examples here. For example, let us say you have a rail gate crossing. So, let us say in this crossing, whenever there is a gate and whenever the train is coming, there is a sensor which is sensing whether it is approaching or not. Okay. And similarly, you can have a sensor to sense whether you have the train have exited or not, right. So, now for the train, gate and the controller, if I am trying to model their behaviors using this kind of timed automata based mechanisms. So, let us say I am creating a train automaton. So, let us say, sorry it took some time, you have these three automatons modeling the train, the gate and the controller. So, let us say initially you are sitting here. So, the train is far away. Okay. So, the train is far away, you are in this state and the gate is open, right. So, let us say you are here and the controller right now is is in this state here. Now, so that's like your state when the train is somewhere here, and let's say now the sensor this sensor goes on with approach, that means the train is nearby, right. So, once the sensor is saying you're nearby, all these states are now going to change, and let's see how. So, when this approach event is true, right. So, due to this approach event happening, that is like an input event coming from the sensor. This train automaton, let us say it is switching to near, okay, and along with that, with this approach is also an input event. So, this question marks model input event, right, and if somebody is outputting an event, it is through an exclamation mark followed by that event. That is a standard which is followed in automata theory in general. So, this controller also then change its state here. Now, you can see that when the train has changed to this state, it has set up a counter, right. So, x is being reset and you can only be in this near state up to this x less than equal to 5, and the controller can also be only in this state up to z, its own local clock less than equal to 3, right. So, it is something like you have a timeline, an approach event has happened and you are monitoring this z less than equal to 3, and also the train must you know that within x less than equal to 5, the train will definitely change from its near state and really enter the gate, right. It will really enter here, and that is known to the designer of the system here. So, next what will happen is the train will come in, right, and in between the controller needs to give suitable commands, right, so that the gate is being lowered. So, before the train moves from this thing, actually the train moves from this location to this enter state, the controller inside a smaller amount of time. So, as you can see that the time given for the train to move from here to here is 5, right, inside after 5 it must be here. So, that is the timing model. So, if you see what we are saying is even before that, the controller within 3 time units it must go to a state where it will signal the gate to lower down. It will signal the gate to lower down, and then it will be in that state, and when this lower signal comes from the controller inside 1 time unit, as you can see because of this clock constant model, inside 1 time unit the gate must move from this up state to the down state. So, you see that is a sequence of events to be modeled. Inside 5 time units from being near, the train should be here inside 5 time units. So, even before that the gate which was raised must go down, right. So, the way it is modeled is inside these 5 two things will happen. Inside 3 time units the controller must come to a state where it is emanating this signal, right, and this signal is an input event for the gate subsystem here. So, the gate system must react to this signal and it should have its internal clock reset, so that and that clock condition here will monitor that the gate must go down inside 1 time unit. So, what this will in effect ensure is that before the train is in, the gate is actually down, right. So, this is how using this an automata model you can create the specification of a timings of a real time system, and just like we did reachability analysis, there exists similar techniques, there exists well known logic based or algorithms through which you can actually use several automated decision procedures to check, well, if you have a real time system for which you have a timed automata based model, whether that system works correctly, whether that system is safe, whether that system satisfies some timing specification and all these things. So that's one primary reason why people use this kind of models. Model usage also is another important reason. There are tools which support these models, and they can do code generation for the source models using several kind of modern embedded system design tools, more for model based design primarily. So let's see that how these things will move. Now what will happen is, inside this time the controller will move from here to, like I was saying, it will move to this, and once it has shifted to this, the gate will move from up to this, and then inside this timeline, as I was saying, it must go to the down step. Okay. So here inside this 3 time you will have this lower signal coming, and then inside some y equal to less than 1, starting from here, inside this interval you will have the down event really occurring, right. So and then at some time the train will actually enter, and before that the gate is actually down here. So eventually what will happen is the train will come here, and by that time the controller will ensure, this gate's downward movement has created this down event to happen before the enter event, right. And then if you see that the train has entered, and eventually the train is supposed to leave, right. So when this train is leaving, what will happen is it will give this exit signal, right. And once this exit signal is given, it's like an input for the controller, right. So with the exit signal, the controller will move to this state, and as you can see that here again it's reset a clock, right. And inside 1 unit of time of getting the exit signal, the controller will output this raise signal, right. And this raise signal is basically an input for the gate's physical subsystem, right. And with that, after getting this raise signal inside this 2 units of time, you have a resetting and you have a guard, the gate will go to this up state, right. So once it has exited, it gives the raise signal based on the exit event, and inside after some time within this 2 units of time of getting the raise signal, the gate will go to an up state. So that's how it works here. So let's check another simple example. Suppose you are given another real time system specification for, let's say, an elevator system. So you have an autonomous elevator which operates between 2 floors, and it is supposed to have the following behavior. The elevator can stop either at the ground floor or at the first floor. Now when the elevator arrives at a certain floor, its door will automatically open, and it takes at least 2 seconds from its arrival before the door opens, but the door must definitely open within 5 seconds. Now whenever the elevator's door is open, passengers can enter, they enter one by one, and we assume that elevator has a sufficient capacity to accommodate any number of passengers who are waiting for it. Of course that's not an ideal scenario here, and whenever the door is open, passengers can enter, and they can enter one by one, just like that. Sorry, we have a repetition here, so you can just ignore this thing. Okay. And then the important timing behavior you have here again, that the door can close only 4 seconds after the last passenger has entered. So once the last passenger has entered, the door can close again, and after the door closes, the elevator will wait at least 2 seconds, and then it will just travel up or down to the other floor. Okay. So let's say you just want to create a timed automaton, and you are using these actions up and down to model the movement of the elevator, and open and close to describe the door operations and the action enter, which will mean that the passenger is entering the elevator. So, as you can see, it is very easy actually. What you can do is you can have a state. So, let us say here passengers are entering. So, there is an enter event, okay, and let us say this is representing floor 1, and then eventually there will be an up action, you will move, right. So, if you check our constraints like earlier, so the door can close only 4 seconds after the last passenger has entered, right. So, after the passenger has entered, the door will close. So, you can put a constraint like x greater than equal to 4, and this is the guard which must be satisfied, right, with the close event. And then while this happens, you can take a reset of this clock. So, if you look at this, the elevator arrives at the floor and the door opens, and exactly and that would happen inside 2 seconds of its arrival, right. So, that also we have to model, and it should happen between these 2 and 5 seconds, should at least take 2 seconds to open, but it should open within 5 seconds. So, these are the 2 kind of constraints we have, right. So, I think with all these constraints we can just model them like this. So, if you just check once again, so we have this as a floor 1 state, and this is the floor 2 state, and these are the in between states we have drawn, right. So, passengers entering is considered here as an event, right. It can stop either of these floors. So, when an elevator comes, right, this is where we say that it has arrived, right. Now, once it has arrived, it is going to take the door can close only 4 seconds after the last passenger has entered, right. So, that is modeled here, right, and after the door closes, the elevator waits at least 2 seconds. So, it will just wait at least 2 seconds, right. So, only after x is reset here, and there in this transition you have x greater than equal to 2, and after that the up action should happen, right, and it will travel upwards, right. Now, it will take at least 2 seconds from the arrival before the door opens, but the door must definitely open within 5 seconds, right. So, that's modeled here, right, and after that the door will open in the second floor. Okay. Now, in the second floor, like you see that the door can close 4 seconds again here after the last passenger entered. So, only after being in this floor and all the enter events, with each enter event I am just looping here, and whenever one passenger is entering, this clock is being reset. After the last passenger is entered, there is no one coming in, so there is no resetting. So, clock will go up, and once it expires 4, then the door will close and I come here, and then from floor 2 I will be starting to go down, right, and once I have gone down, I will again reset, right, and then we will reset and I will move to opening the door inside an interval from 2 to a max of 5. So, that is why 5 is the invariant and 2 is the guard condition, and again the entering logic will be just like for floor 2 in floor 1, right, and again all the passengers get in, then x greater than equal to floor, then I just start going up, and that is how it works. Okay. So, this is a very simple model, but just to incite your mind, there are several interesting problems around elevators that can actually be done. For example, you can have multiple, let's consider a situation, you have say large multi-storied building, okay, large multi-storied building of many floors, and you have 2 elevators running, okay. So, they can both go up and they can both go down. Let us say you are trying to build a control algorithm which is going to control the up or down signals, which is going to give these up and down signals for the elevators, and as a feedback it gets to know what is the current floor information of the elevator, feedback is current floor information of each elevator, and then number of passenger requests for each elevator and current occupancy, passenger requests that are pending for each elevator, current occupancy, etc., etc. So, I can design a central controller which will work in real time based on these feedbacks, and it will decide which elevator goes up and which elevator goes down from which floor, right. So, designing such controllers is a very important real time programming problem, and just to pick your minds, you can think about it. You can design a small simulation C program, or let us say an Arduino based controller of such a toy system, stuff like that. Okay. So, fine, with this we will end this lecture. Thank you for your attention.